Hello and welcome back to Calculus2. We are continuing our chapter 10 exploration. So this is lecture on 3 of the 10 tests. We had the first 2 last time. The first 2 tests were on, what were they on? First 2 tests were on telescoping series and geometric series, and those are the only 2 tests where you can tell what the series converges to. And now we have divergence test, integral test, and piece series. So just to backtrack tiny bit to review what we had so far. Sequence is an ordered list of numbers. It was ordered through the set n, and we had some formula that generates the list. All the values in that sequence were separated by commas. So we would have something like an is equal to, and then a0, comma a1, comma a2, comma a3, comma dot dot dot, going on forever. And the only test for convergence of sequences is the limit test. So you would say a limit as n goes to infinity of an is equal to, and then it either is some kind of L, which is the finite number, in which case converges to L, or it was positive, negative, infinity, or does not exist, in which case diverges. So that was 100% what we did in terms of the test for sequences, just numbers. And that was the story in our first 2 sections of the chapter. Then we moved to the next creature in this chapter, and that creature is a series. Series is a sum of a sequence. So summation an, let's say 0 to infinity, is a0 plus a1 plus a2 plus a3 plus a4 plus dot dot dot, going to infinity. We do have a finite series, we just don't care about them, not because we are mean and evil, because they're not interesting. If you have a finite amount of terms, whether that is 3 or 10,000 terms, you can add them and be done. They all converge every time. If you have a sum, the sum of finite series always, right? So a finite series always converges because you have a finite amount of numbers to add, and again, we don't care whether it's 3 or 10,000 numbers. You add them all, whether it's by hand on the calculator or the computer, whatever way we add, they will always end up being a finite value, so they always converge. Now, infinite series are those that we are interested in, and infinite series can converge or diverge, meaning their sum is either a finite number L or is infinity. Now, they are very tricky creatures, and for most of them, we would know whether they converge or diverge, and if they converge, we don't know what they converge to. We just know they converge to a finite value. Now, the first 2 we covered, telescoping and geometric series, are the only 2 out of the 10 tests that we can use that will tell us what the series converges to. The other 8 tests will not tell us what it converges to. Actually, the first test we're going to talk about today doesn't show convergence at all. It just shows divergence. So actually we have 9 tests that will show convergence and 10 tests that you can use for divergence. So series is the sum of the sequence. The series is the summation of AN, and it means you add all of these. And now we have 10 tests to check convergence or divergence. We already covered 2, so geometric, series test, and telescoping series are the only 2 tests where we know the sum. Other tests will just tell us it converges, but it doesn't tell us what value it converges to. So today on the menu, the first is divergence test. Emphasis on the word divergence, i.e., cannot show convergence. That should be common sense. If the name is divergence test, then it tests for divergence and it moves off. So divergence test. So here we go. This is the part which you are memorizing. So this is the theorem. If the limit of an as n goes to infinity is different than 0, then the series summation an from, let's say, 0 to infinity or 1 to infinity or whatever to infinity, an diverges by divergence test. That's it. So you get, let me just write one more thing. Otherwise, test is inconclusive, in parentheses, use something else. And I'm going to underline the word otherwise, because if you get that the limit is equal to 0, means nothing to you. It does not mean convergence. Don't play with fire. So here are few examples. Each example is about 7 seconds. That's all it is. Series of n plus 3 from 2 to infinity. You say limit n plus 3 as n goes to infinity is equal to infinity, which is different than 0, it diverges. Done. Next example. Summation, let's say 0 to infinity of 1 over n plus 3. We go limit n goes to infinity, 1 over n plus 3 is equal to 0. Inconclusive. Can't use this test. I have to go something. If it's equal to 0, move along. summation 3 1/4 to the n, starting at, let's say, 2 to infinity. Well, you say limit n goes to infinity of 3 over 4 to the n equals 0. Inconclusive. This test doesn't help us. What is this? What is this one? You should know this one by now. We learned it last class. This is geometric series. Your r is 1/4. It's less than 1. Therefore, it converges by geometric series. But the divergence test is inconclusive because the limit was 0 and the convergence test has no clue what's happening here. Divergence test cannot show convergence. Let me spell that out. Divergence test cannot show convergence under any circumstances. It is the only test the way it is, and that's the end of the story. So that's divergence test. You take the limit of the sequence. See, when I write summation of an from, let's say, 3 to infinity, this part alone is sequence, and then together is a series. So when any time I write a series, the sequence an is within it. And if you take the limit of the sequence, if the limit is not 0, anything but 0, you can get 3, you can get 7, you can get infinity, then it's divergent immediately. The next test is integral test. Now, this test is packaged with a lot of algebra, and you need to check the conditions first in order for integral test to be used, and then whatever the conclusions of the test are is what you get. The idea starts when we talked briefly about an equals 1 over n and f of x equal 1 over x. If you remember, at one point I said their graphs coincide, where the f of x has these continuous lines, the discrete an would just have these dots. But they happen exactly on the line. So this is either x or n, depending on which one you look at, and your number 1, number 2, number 3, number 4, number 5, going on forever. There is nothing for an on this side because n's start at 0 or 1. In this case, they cannot start at 0 because you would have 1 over 0. So they start at 1. So this is the first value, n equals 1, which is n equals 1 here. And then n equals 2 gives you half, n equals 3 gives you 1 over 3, which is a third, n equals 4, 1/4, and so on. So we see them diminish together. Integral test is trying to compare these two worlds and say, you know what, when these three conditions are satisfied about the function you claim you have, then you can use improper integral to talk about convergence or divergence of a series. So the theorem goes like this. If f of x is, number one, continuous, number two, positive, number three, decreasing. So if these three conditions on f of x are satisfied, and you converted your an into that f of x, then series of an that goes to infinity, and the integral, I'll put some value a on the bottom, so a to infinity. They start at the same number. If the series starts at 2, integral starts at 2. If the integral starts at 7, if the series starts at 7, integral starts at 7. So that a value on the bottom is the same value. F of x dx, both converge or diverge. So they share the same fate if those three conditions are satisfied. So your 1 over n becomes 1 over x, and if we are able to establish those three to be true for 1 over x, then we can do the integral, and whatever integral tells us, that would be the situation we have. So that's called integral tests. Now it comes in with these, oops, I've dropped the u over here, continuous, there we go. So we have to solve these three conditions and show that these three conditions hold, and then we can do the rest. So let's try and figure out what's happening with 1 over n. Series 1 over n from 1 to infinity. Now this is adding all these numbers. 1 plus a half plus 1/3 plus 1/4 plus 1/5 plus 1 over 6 plus going on forever. Question is, does this sum converge or diverge? All right, so 1 over n is a discrete function. It only has dots. So that's my an is 1 over n. I want to transform that into f of x equals 1 over x. And now I need to show that three conditions hold. Condition number 1, is it continuous? Well, if you are able to draw a graph for this and just show that three conditions are satisfied on the graph, and it's, obviously easy to see it, then you are done. So you have to make sure that you limit your domain to the domain that is provided by the series. Your series starts at 1 and goes to infinity. So your integral must start at 1, and when you draw the graph for 1 over x, you will ignore anything left of 1. We all know the graph of 1 over x contains these two parts of the line. However, the series starts at 1, therefore we only care about this part. We do not care about anything before that. We only care about the part of the line that is given by the domain, the restricted domain imposed by the series, which are these two over here. So now, you are going to look at this piece of the graph and say, is it continuous? Yes. The only vertical asymptote you have is at 0, which is the interruption in the domain in continuity, but that one is not included from 1 to infinity. So there are no interruptions of any kind from 1 to infinity, therefore it's continuous. Number 2, is it positive? Meaning, is it above x-axis? Above x-axis. Yes, it is, because look at it. It doesn't go under the x-axis at any point in time. It's always positive. Number 3, is it decreasing? Yes. And I keep pointing to the graph because this is a joke of a graph that you can draw. You all know it. So all of these are yes by simply looking at the graph. Now, can you actually solve these? Well, sure you can. Continuity, you have continuity that you use those proofs from Calculus2, where you say all polynomials are continuous. Quotient of continuous functions is a continuous function provided denominator cannot be 0. 0, which would make our denominator 0, is not in our domain, therefore denominator is never 0, and this is continuous function. It's a very simple paragraph that you write to prove that it's continuous. Now, positive. This means, are all of my values positive? Sure they are, because your domain are only positive numbers. When you divide 1 by a positive number, you always get a positive number. Therefore, all y values for this function are always positive, because positive divided by positive is positive, and all of the values are positive, therefore positive works as well. That's the proof. And number 3, is it decreasing? Well, you can just take the derivative and show that the derivative is negative. Negative derivative on that interval is obviously showing the decrease in a function. So there are a few ways in which you can do all of that. So now that we established yes, yes, and yes, all 3 of these conditions have to pass, then we can look at the integral 1 to infinity of 1 over x dx. So that is the integral that we get to solve. It's an improper integral. Just had the exam on improper integrals, so you know that you are supposed to go limit b goes to infinity, integral 1 to b of dx over x. You will get limit b goes to infinity of ln of absolute x from 1 to b, and you will get finally limit b goes to infinity ln of b minus ln of 1, which goes to 0, and we get a big fat infinity, which is divergent. So now you are ready to write the answer to the question. If you want the full credit, right, for all this hard work, you have to provide the answer. Since all 3 conditions hold and integral 1 to infinity 1 over x dx diverges, series summation 1 over n from 1 to infinity diverges by integral test. This sentence is not optional. This sentence is the answer for the problem. And this sentence will be part of every answer on the next exam when you have only series. Your job is to solve the problem and then provide the answer, whether converge or diverge, in the sentence at the end. All 3 conditions hold. You will have conditions for alternating series test. You'll have conditions for comparison tests, right? So they will have conditions. And you say when those conditions hold and whatever else needs to happen, in this case, that integral diverged, you are going to see that the series will diverge as well, which is what I meant earlier when I said they share the same faith. No one cares about your integral answer. No one even asked you. Nothing about 1 over x, all right? These are all the means that you had to employ to get to the answer that the people care about, right? This is a computer science world, discrete realm. There is no 1 over x in computer science. You have discrete values. It's ones and zeros. It's on and off. Ticks all the time, right? There's no continuity. So what you do is some problems can be solved by comparing the series to an integral, because we know that the integral is a summation, right? The Riemann integral, we learned that. So we compare these two functions, the discrete function an to a continuous function f of x, but those three conditions have to be checked. Now, what we discovered here is that the series 1 over n is divergent. So these are the things that you guys have to sort in your head now, because it is important. Here we go. Sequence an equals 1 over n is convergent because limit of 1 over n as n goes to infinity is equal to 0. So if you are only talking about sequence, and that's 1, comma 1/2, comma 1/3, comma 1/4, and so on, then it's a convergent sequence. Series summation 1 over n diverges by integral test. Now, this series is a very important series that will come back many times in this and the next chapter. We have a name for this series. It's called Harmonic Series, and it is good practice to memorize today that harmonic series summation 1 over n diverges. So this series here is called Harmonic Series, and it diverges, and we just did the proof to show that it diverges by integral test. We can do the integral test and show that it diverges. This is my attempt here in blue to show the difference between sequences and series. Sequence is a list of numbered, ordered list of numbers. Series is the sum of that list. They're not the same. And you see now that you have 1 over n and 1 over n, sequence converged and the series diverged. So you don't get to mix them. They have their own worlds and they have their own tests. And you just have to sort this in your head and say, for sequences, all sequences, I only have one test. That's what I said at the beginning of the class. One test and one test only. And that's the limit test. You hit your sequence, the formula, with the limit, and whatever happens on the other end. Series will have 10 different tests that you can try. And you should regard these tests just like you did different methods of integration, different methods to take derivatives. You take a look at a problem, you say this is a product rule. Now you will take a look at a problem and you will say, oh, this is integral test. Or, oh, it's P-series. Oh, telescoping series. Right? So there is a learning curve there, obviously. And just as you have, as I said, different methods for derivatives, product rule, quotient rule, chain rule, logarithmic differentiation, implicit differentiation, or basic ones. Now you're going to have, and then you had all the right basic by parts, and then U sub, trig sub, partial fraction, right, for integration. Now you're going to have the same thing for series. 10 different methods. You apply whichever one is appropriate at what time. Another example of integral test. What is happening with summation of 1 over n squared from 1 to infinity? Well, we do the same thing. We extract that an, which is a sequence, is 1 over n squared, from where we claim that f of x is equal to 1 over x squared. Now, if you don't know the graph for this, you should, but if you don't know, the graph looks like this, but let's say we don't know it. We need 3 conditions to hold in order for us to have this work out. Number 1, continuity. Quotient of 2 continuous functions is a continuous function. Continuous function if denominator is not equal to 0. Well, note that the domain is again 1 to infinity, so 0 is excluded. 0 is the problem point. So since 0 is not in the domain, which is 1 to infinity, 1 over x squared is continuous. That is us checking off number 1. Number 2, by the way, it doesn't matter which order you do this. You can do positive or decreasing or continuity. Any order is fine. None of them depend on the others. And either one can fail, or all. They can all fail. Positive. We can just simply say, because we are considering f of x 1 over x squared, we can just say quotient of 2 positive numbers is always a positive number. And we're done. Because anytime you have a number that is squared in denominator, it's positive. Take any value, positive or negative, doesn't matter. You're just not allowed to use 0. But, however, we are only as input using numbers from 1 to positive infinity. So any number you square is still positive, then 1, which is positive, divided by whatever you have, which is always positive, is going to be positive. So we just checked off number 2. Number 3, is it decreasing? There are 2 ways in general to solve this. One will be using calculus, using derivative, and the other one is using basic algebra to show that the sequence is decreasing by showing that the next term is the smaller than the previous term. Because if the next term is smaller, well, that means it's decreasing. So we can use a n plus 1 needs to be less than an. So that's the next term because it's plus 1. So you can either do that or f prime less than 0. So you can do this either on a sequence or you can do it on the function. Whatever. Let's use the function. My function f of x is 1 over x squared, which is x to the negative 2. F prime is going to be negative 2 x to the negative 3, which is negative 2 over x cubed. Since x is always bigger than 1, that's noted in the domain 1 to infinity, all x cubed values are positive. So negative 2 divided by positive equals negative value, meaning that f prime is always less than 0 on 1 to infinity. That implies decreasing. You learned this in your Calculus 1 when you learned your first derivative test. You learned in the first derivative test that if the derivative is negative, function is decreasing. If the derivative is positive, function is increasing. So this is over here using that to prove that the function is decreasing. So now we have checked off number 3. Since all 3 conditions hold, I can, instead of writing the summation, I can use integral 1 to infinity of 1 over x squared dx. This is limit, right? It's improper integral. B goes to infinity. And then we have integral 1 to b of x to the minus 2 dx, which is the limit. B goes to infinity. And I have integral of this is x to the minus 1 divided by minus 1, computed from 1 to b. Further, this is limit b goes to infinity. Now we're just doing basic integration. This is a negative 1 over b. Minus and minus gives me plus 1 over 1. So when b goes to infinity, this is 0 plus 1 equals 1, converges. Integral converges. This means that the series converges because if the 3 conditions hold, they share the same fate. If the integral converges, series converges. So now you get to write the same sentence as earlier as answer. Since all 3 conditions hold and integral 1 to infinity of 1 over x squared dx converges on 1 to infinity, the series summation 1 to infinity 1 over n squared converges by integral test. This is the answer you are providing for full credit. The sentence must be there. I already used up red, so I guess I go blue. Common mistake. Stay away. The series and integral do not converge to the same number. Your integral converges to 1. The series doesn't converge to 1. All right? So the sum of the series, we don't know. We just know it converges. Integral converges to 1. We don't care because it's not the same value. So please try to avoid writing that the series converges to 1. No, integral converges to 1. They are not the same. They both either converge or diverge, but convergence, different values. When you see an given in a light where you can integrate, then the good way to solve it is by integral test, but only if the three conditions hold. Sometimes troll questions on the exam are, use the integral test to test the convergence of the series. Boom. And those who don't pay attention, what do? Integral 0 to or 1 to blind, just go. Boom, converges at the end, move to the next problem. But I did say troll question. One of the three conditions didn't hold, so 100% of what was written is garbage, right? You cannot use integral test at all if one of the three conditions fail. You can try something else instead if it's available, possible, but if it's not, then you can just cry. That's what it is. Certain functions cannot be integrated, use numerical methods. Same for sequences and series, right? For series, if none of the tests work, maybe you can write a code, and add 10,000, then add 20,000, then add 100,000, then add million members. See if they all give roughly the same number, because that means it might most likely converge. Not guaranteed, but most likely would. But make sure you are not confusing those two. Now, from these two examples, where we said that the summation of 1 over n diverged and the summation of 1 over n squared converged, we are going to come up with something is called P series. And this is the cheapest, absolutely cheapest test that you guys can possibly have. And it goes like this. Summation of 1 over n to the p. So p is the exponent of n. P is the exponent of n. It has to be in denominator. From 1 to infinity or 2 to infinity, whatever. Just make sure it's not 0 in denominator. And here we go. P less or equal than 1, divergence. P larger than 1, converges. Done deal. That's the whole test. You look at it, you look at the value for P, just like you look at the value for R, right? Geometric series, value of R, is it between -1 and 1 converges? If it's outside of that, or 1, diverges. Well, this one is reversed. Divergence is less than 1, and greater than 1 is the convergence. And you can see quickly that 1 over n squared, P is 2, 2 is bigger than 1, that converges. So immediately, 1 over n cubed, 1 over n to the 4, they all converge, all of them converge. The 3 halves, P equals 3 halves, convergent. p equals 2/3, divergent. So you just look at it. So let's say you have summation 1 over cube root of n squared. Well, you will write this as summation 1 to infinity of 1 over n to the 2/3, 2/3 less than 1, divergence done. So maybe you have to write one step, right, to really strain your arm, right, to solve this type of a problem, which is why it's so important to understand that memorizing these tests is the first step to do anything in this chapter. If you don't know these tests by heart, you cannot solve these problems, and you cannot make it up. Because you saw 1 over n converges as a sequence, diverges as a series, then 1 over n squared converges as both, right? Trying to memorize this example by example is just a living nightmare. So learning the tests is crucial. So having these handy, knowing, what the P is, what the R is, what the A is, shift the counter, all that stuff. That's P series. So you just look at P and determine whether it's smaller or larger than 1, and you are on your way. We have time for another integral test. So today we took care of 3 tests. Tomorrow, I noticed that I'm missing a day over there. This is Monday, and this is Tuesday. This is Wednesday. But I noticed that there are more chapters, so more sections. So 10.6, 10.7, 10.8 lab, chapter 11. So everything stays the same. We just have 10.8 is one of those. You had one of those sections just like for integration where you say, let's just have a whole bunch of problems on a pile, figure out how we sort them out. Which test should I use? Just like for integrals, you look at the integral and say, it's trig sub because I have a square root. Right? The problem I kept changing over there. I just hope you didn't use trig sub on it, which is why there was a smiley there. Right? Yeah, it was basic U sub. It's x on top and then x squared on the bottom, so it's a basic U sub. Anyway, I know it hurts. Another integral test problem. Pick something from homework. That problem was also at the same time it was a basic U sub, but it was the type 2, right? It was a mess of a problem. Integral test. Beautiful problem 26. It says, now they use K's all over the book. I don't care whether you use M, N, or K. And some schools even use L. So I grew up using N. So most of these problems I teach and I write with N, but this particular book loves K a lot. Everywhere. Everything is in terms of K's. It doesn't matter. This is a problem. You look at this problem and you say, aha, I have n cubed in denominator, n squared upstairs, I can do U sub, right? So it seems that I can integrate this. If any of the 3 conditions fail, I have to abandon this method. So now I need to show 3 conditions. Because my goal is to, so let's first an is this, and now transferred into f of x as x squared over x cubed plus 5. So is it continuous? That's number one. Well, yes. We have, yes, we have division or quotient of two continuous functions. Guys, both of these are polynomials. They are continuous everywhere. There is a theorem in Calc 1 that says all polynomials are continuous on the entire domain. So, right, all of these problems. And if you have a cube root of -5, but see, that's a negative value, and that's not going to be included, right? The problematic point. So, continuous functions, and all of the values in the denominator are always positive, because quotient of two continuous functions on 1 to infinity. What would make it discontinuous? A very special point, right, which is a cube root of -5. That would make it discontinuous. But cube root of -5 is a negative number. It's not in the domain here, so we don't have to worry about it. We're all good. Continuity, pass, move to positive. Okay, positive. We have x squared is always positive, because you square any number, whether it's positive or negative, when you multiply a number by itself, it always makes positive numbers. That's basic. Now, x cubed is always positive on 1 to infinity, because 1 cubed is 1, 2 cubed is 8, anything in between is also positive. So when you cube a positive number and you have positive input all the time, all of the values are positive. So now you say quotient of two positive numbers is always positive. And that's us checking off positive. Decreasing. Is it decreasing? Well, you know what? Last time I used the derivative. Let me use this time to show that an plus 1 is smaller than an. If it holds, right, because we can do it this way as well. You can go and take the derivative, show the derivative is always negative, whatever makes you happy. So I have my an as n squared divided by n cubed plus 5. My an plus 1 is going to be n plus 1 squared divided by n plus 1 cubed plus 5. And I need to show that this is always smaller. All right, so I'm going to have my n plus 1 squared over n plus 1 cubed plus 5 needs to be smaller than n squared over n cubed plus 5. So if this holds, it will show that the next term is always smaller than the previous term, meaning decreasing. Okay, so what can I do here? Well, we can FOIL these first and then cross multiply, and we can compare them term by term, right? So if I cross multiply, first I have my n squared plus 2n plus 1 times n cubed plus 5. That should be smaller than n squared times, this is n cubed plus 3n squared plus 3n plus 1 plus 5 is 6. So now you keep foiling. You have n to the 5 plus 2n to the 4 plus n cubed plus 5n squared plus 10n plus 5 needs to be smaller than n to the 5 plus 3n to the 4 plus 3n cubed plus 6n squared. And here is the moment of truth, right? When these guys drop, because they are the same, you are comparing the highest terms of 2n to the 4 to be smaller than 3n to the 4. And that's a true statement. Since that is true, that means that the inequality we were looking for holds, which means that we have a decrease, right? Because the inequality was true. Or you can take the derivative. Show it's always negative, whatever. So we just show that decrease works. This means that I can go 1 to infinity n squared over n cubed plus 5, not n, x. dx, which is the limit. X goes to, b goes to infinity. 1 to b, and then I have x squared over x cubed plus 5 dx. It's a u sub, so u equals x cubed plus 5. du equals 3x squared dx. I don't have a 3, so I'll put these 3 and 1/3 to make u sub work. This is equal to the limit b goes to infinity. 1/3 of the integral is simply du over u. And if you want to, you can change your limits, but it doesn't matter. Limit b goes to infinity. It's not going to work, obviously, because ln of infinity is infinity, so you're done. Limit of 1/3 of ln of absolute u, which is x cubed plus 5, computed from 1 to b. And we get infinity, which means diverges. So now I'm going to write the answer. Since all three conditions hold, and integral of x squared over x cubed plus 5 dx from 1 to infinity diverges on 1 to infinity, the series summation 1 to infinity of n squared over n cubed plus 5 diverges by integral test. So we use integral test to show all of the p series and to solve all of the problems where we can integrate. The sentence at the end is considered the answer for this problem. Again, no one cares about your convergent or divergent integral, right? The question was what is happening with the series. You are using integral test as a means to get to the red sentence, which is the actually answer to the question. So I hope you will, sit down and sort these things in your head. Tomorrow we have comparison tests and alternating series tests. So tomorrow we are discovering another 3. We are at a half now. We took care of 5. Geometric, telescoping, divergence, integral, and p series. So we did 5 out of 10. It's a halfway. Tomorrow we do another 3. comparison, direct comparison, limit comparison, alternating. And then we are only left with root and ratio for Wednesday. See you all tomorrow.